Hello and welcome to video for the methodology 9.2, where we apply the Laplace transform technique to a differential equation with a piecewise forcing function. Our instructor model example, the differential equation is y double prime plus y equals this piecewise function f of t, where the function is equal to 3 when t is between 0 and 4, and equal to 2t minus 5 when t is greater than 4. And we have initial conditions that y at 0 is 1 and y prime of 0 is 0. Step 1 in the methodology, we will write the piecewise forcing function in terms of unit step functions. So we want to be able to write the whole differential equation in a single line instead of having this kind of two rows format that we have with normal piecewise function notation. And since we're only concerned with this differential equation when t is greater than 0, we don't really need the unit step function around the first piece. And so we start by just writing the first piece, which is 3. And usually these pieces are arranged so that going from top to bottom, the subsets of the domain are increasing, but you want to make it that way if not already. The second piece is trickier. We need to add on the second piece, but then we also need to subtract the first piece. And then we need to put a set of parentheses around that whole thing and then put a unit step function on it for, in this case, 4, but wherever the pieces transition from one to the other. So since the first piece is t less than 4 and the second piece is t greater than 4, our unit step function steps up at 4. I notice that if you evaluate this function when t is less than 4, the unit step function is 0 and you just get 3, which is the first piece. If, however, if you evaluate the function when t is greater than 4, the unit step function will be 1, and you'll have everything you see here, and the 3 and the negative 3 will add to 0, and you'll get the 2t minus 5, which is the second piece. So this is equivalent to the piecewise function, but written in a form that's more convenient for taking the Laplace transform. Now we can simplify that to 2t minus 8, but we'll just do that in the next step. All right, so now we're going to apply the Laplace transform to the differential equation. And then we can distribute it using the properties of linearity. So we get the Laplace transform of the second derivative plus the Laplace transform of the solution. And then here, we're going to have the Laplace transform of the result from step 1. And so we can do that simplified version here. And you can also use the subscript notation for these unit step functions if you prefer. So the Laplace transform is being applied to that whole thing. All right, let's do the left side first. We're going to use the formulas for the Laplace transform of the second derivative. We don't have the first derivative here. So let's go ahead and remind ourselves what that is. So it's s squared times big Y of s, where big Y of s is the Laplace transform of y, minus y prime of 0, minus s y of 0. I don't know why I tried to put that off to the side. That just still gets in the way. Let's just put it front and center. So we're going to use that expression, that formula, but we know our initial conditions. So we can actually make it specific to this problem. I mean, that first term is always the same, but y prime of 0 is 0, so you get minus 0, which will drop, and then minus s times y of 0, where y of 0 is 1, so we get minus s. So this s squared times big Y of S minus S will be substituted in for Laplace transform of y double prime. So then we get S squared big Y of S minus S plus, and then the Laplace transform of Y is big Y of S. And we can go ahead and distribute the Laplace transform here. Why not? And where we're headed with this, you can see in step 5, we're going to solve for big Y of S, which only appears on the left side. So you can actually go ahead and factor that here. All right. When we get to step 4, we're going to take the Laplace transform of the right side, and that 3 is no problem. Laplace transform of 1 is 1 over S, so the Laplace transform of 3 is 3 over S. However, the dealing with unit step functions is tricky. That's what's new to this methodology. And you notice that we really want to identify that A value. In fact, let's use a different color there, A, because that appears in the exponential, base E, and in the shift in this formula. And so for us, it's 4. A equals 4. You can also see that f of t is 2t minus 8. So we're going to apply this formula using those values. So here we said Laplace transform of 3 is 3 over s. All right, so we're going to replace the unit step function with an exponential base e, and then it's negative sa as the exponent. A is 4, so negative 4s. And then you still need to take the Laplace transform of the function, but you have to shift it first. And you shift it by adding a to t. So we need to take any t, which we have just the 1, and replace it with t plus a, which is t plus 4. So that's f of t plus a, right? And that could then be simplified. 2 times t is 2t, 2 times 4 is 8, 8 minus 8 is 0. And so you just get the Laplace transform of 2t here. And the Laplace transform of t is 1 over s squared. So the Laplace transform of 2t is 2 over s squared. So that just turns into a 2 over s squared. There with the exponential. All right. Now we're ready to move on to step 5. Let's get rid of this stuff. And you notice that, when we did the shifting, we replaced t with t plus a. If t does not appear in your function, if it's a constant, then you don't have to shift, right? You're just replacing the independent variable with that shift. All right, so step 5, we're going to solve for big Y of s, which is the Laplace transform of the solution. And what we're going to do is add s to both sides. So we'll get a plus s on the right, and then the minus s disappears on the left. And then we're going to want to divide both sides by that s squared plus 1. So when you have these rationals, just go ahead and put that extra factor in the denominator. We don't want complex fractions. All right. So that's it. All right. Tricky part is step 6. I mean, we just need to take the inverse Laplace transform of this. But of course, our technique for doing that is to use the table. And you're looking at these expressions on the right. That one on the far right, s over s squared plus 1, I mean, that's in the table, right? Quickly go to the table. S over s squared plus 1 is cosine. So we're good there. But the 3 over s times s squared plus 1, not there. And the 2 over s squared times s squared plus 1, also not there. So those kind of complicated denominators need to be broken up via partial fraction decomposition. So we'll need to break both of those up. Let's start with the 3 over s times s squared plus 1. So we're going to break that into a over s, and then bs plus c over s squared plus 1. And then if you multiply through by the common denominator, which is the s times s squared plus 1, get all the fractions cleared away. And then we just need to figure out these unknown coefficients a, b, and c. So there's 2 ways of doing this. You can put in specific values of s, and the way that might work is you'd say, oh, what if s equals 0? If s equals 0, this actually simplifies into 3 equals a. And if you can't do that, which you can't always because the roots of some of these are imaginary, right? The other technique is to expand it out, which we can put that 3 in there now. So distributing here. And then you can set up or equate like terms. So you can get an equation for the s squared terms. There's no s squared term on the left, so it's kind of like there's a 0 s squared. So 0 equals 3 plus b, right? So those are the cubic, sorry, the quadratic terms. And this tells you that b equals -3. For the regular linear terms, again, there's a 0s there. 0 equals c, and that tells you that c equals 0. And then the others should match up too. 3 equals 3. All right, so we have our values for a, b, and c. Where a was 3, and then b was -3, and c was 0. And these are both ones we can take the inverse transform of. We just have to get those 3 and -3 coefficients brought out front. All right, so that's good to go. What about this one? So that s squared makes it different. When you have that s squared, when you have like a factor squared, you need to have it appear once regular and then again squared. One of those kind of tricky parts of partial fraction decomposition. All right, so multiply through by the common denominator. And we can pick specific values of s here as well. Again, picking s to be 0 is kind of the only one that's helpful. And if s equals 0, then you just have the b part. And it'll tell you that b equals 2. Expanding out, we'd get as cubed plus as plus 2s squared plus 2. Remember, b is 2. Plus cs cubed plus ds squared. So starting with s squared, or sorry, with s cubed, you actually can't get because you've got a and c. So a is the opposite of c. But if you start with the s squared, you get 2 plus d equals 0. So d equals -2. And then if you use the linear terms, you just have the a over there. And since a is 0, that implies that c is also 0. All right. So our decomposed form, we don't have that first fraction, a over s, we just have the 2 over s squared, and then minus 2 over s squared plus 1. All right, now we put this all back together. We get the first fraction is 3 over s, and then you get minus 3s over s squared plus 1. And then e to the -4s, 2 over s squared minus 2 over s squared plus 1. And then plus s over s squared plus 1. Now that you have like terms here, those are both s over s squared plus 1, and it's like -3 plus 1, which is -2. So we can combine those by just adding that one to this one, and it goes from -3 to -2. All right, now we're ready to do step 7, which is to take the inverse transform. You need some more room for this, though. Huh? Right, so when we go in and take the inverse transform, it's going to be the inverse transform of the whole thing. The inverse transform of big Y of S just gives you Y of t. When we do the inverse transform of 3 over S, remember the inverse transform of 1 over S is 1, and so the inverse transform of 3 over S is 3. And then the inverse transform of S over S squared plus 1 is cosine, right? Because S over S squared plus 1 is this formula here with omega equal to 1. So that'll give us a cosine. But there's a -2 there, so -2 cosine. So that covers the first two terms. Now with the last part, with the exponential, remember the exponential came from the unit step function. And so it's going to come back as the same unit step function so that we get a piecewise solution. And again, you're going to identify A, those should be the same A value as before. And so we can see here that A equals 4. And then you're going to take the inverse transform of the function and then shift by subtracting A. So we need to take the inverse transform of those pieces. Inverse transform of 2 over s squared, well, the inverse transform of 1 over s squared is t, and so 2 over s squared should be 2t. And then for the 2 over s squared plus 1, that's going to be sine, right? Using this, where s squared plus 1 is s squared plus 1 squared, so omega is 1, and then we just have the negative 2 out front. So that's going to be negative 2 sine. All right, so the unit step function comes back oops, as a t minus 4. And then if we just take the inverse transform, we get 2t minus 2 sine t. So that's f of t, right? And we want f of t minus a, so each of the t's needs to be replaced with t minus a, which is t minus 4. So how it actually looks after the shift is 2 times, in parentheses, t minus 4 minus 2 sine parentheses t minus 4. And then you can simplify, well, you can't, right? You could distribute that, but it doesn't really help. All right, so that's our solution with the unit step function. If we want to go back to piecewise form, the first piece is just the part outside the unit step function, right? So we'll put the 3 minus 2 cosine t, and that's when t is less than 4. Because when t is less than 4, the unit step function is 0, and all that other stuff's gone. Now, for the second piece, it's not the second part of that result in step 7. It's actually the entire thing. Because again, if t is greater than 4, then the unit step function is 1, and you just have all this stuff. So you just write the entire thing, but you drop the unit step function because it's turned into a 1. And so that we could take the 3 and then the negative 8 and combine them, but it's not really worth it. That's a little too close. Let's back that up. So there's the piecewise form of the solution. And when we talk about validating, we would validate one piece at a time just because of, again, how are you going to type something like that into technology? So we'll think of the solution as just being the first piece, and then it should match up with the first piece in the forcing function in the original ODE, and then same for the second piece. Remember that the original ODE is up here. It's second derivative plus the function. And so we'll take the piece and we'll do second derivative plus the function, and that should give us these two pieces here. So we'll watch for the first piece being 3 and the second piece being 2t minus 5. And we'll just use technology here. So I'm using SymPy, and I'm going to go ahead and put in my independent variable is t. And then I'm going to say that y is the solution. And I'm just going to use that first piece, which was 3 minus 2 cosine t. And then we'll go ahead and just put in the left side of the differential equation, which is second derivative. And then we are adding the original function y. And then we're doing a simplify on that. So that's the left side of the differential equation with the first piece of the solution. And it should give us the first piece in the right-hand side forcing function. Let's see. All right, where did I mess up? Oh, all right. So my derivative, I need to put, I'm taking the derivative of y with respect to t, and I'm doing a second derivative. So remember, 3 was the first piece of the forcing function, so that checks out. Let's go ahead and just modify that. So now we're going to add on the rest of it. Remember, the second piece had the same part as the first piece, but then it had that extra stuff. 2 times quantity t minus 4, and then 2 times sine quantity t minus 4. And the last line of code stays the same because the differential equation, the left side is the same. And then that gives us, so those are the two pieces in the forcing function, 3 and 2t minus 5. So that validates the solution, which is step 9, and we are done. So you're ready to go on to the fill in the blanks and your turn examples. And I'll see you in the next video.